So we are discussing the plane and traveling waves, especially solitons. So suppose we have a PD involving two variables. The two variables are x and t, which are real variable. A solution u of the form given by uxt equals some another function v x minus sigma t, where this sigma is a speed and v is a profile. We call this traveling wave solution or traveling wave profile here v. Here x is and x and t are again the real number. So in general, if we have the tuple x component x1 up to xn, and we can say the um, solution u can be written in terms of vector form inside here y, the scalar product of y and x minus sigma t with the velocity profile here. Okay, so this solution is called the uxt in terms of v y dot x minus sigma t. This is called the plane wave with a wave front. It is normal to y. Uh, the speed here is sigma over absolute value of y, and profile is v here. Solitons. Let's go and discuss the solitons. What is soliton? Let's start from the KdV equation. KdV equation is of the form u sub t plus 6 u u sub x plus u sub x x x. That means this is a nonlinear differential equation. The higher order here is, you can say 3 here, and u is differentiated like three times, or what you call ux differentiate by, again with respect to x you will get uxx, again differentiate you will get uxxx, and here is the product u and ux, u sub x here, so that makes the nonlinear part here. And in r cross 0 and infinity, so time is non-negative, so we can say time is from 0 to infinity and x is some real value. So this is a nonlinear dispersive equation in a model for surface wave in water. Now we seek a traveling wave solution having this structure that we discussed above, like this one. So we are seeking the solution for a plane wave solution. We can say a traveling wave here. So we seek a traveling wave solution having the structure uxt equals vx minus sigma t. Then you solve the KdV equation one here. Provided this v satisfies the ODE. The ODE is given by this one. If you have s equals x minus sigma t, then we have v equals x minus sigma t. So plot this value with different derivative, and now one becomes this one. The ut, this means the derivative of u with respect to t, is derivative of v with respect to t. So this profile with respect to t gives us b prime s. S is x minus sigma t multiplied by, we use general, then there will be negative sigma plus 6 is a constant. U replace u by v, b function of s, and ux is b prime of s with respect to s. And u sub x x x can be replaced by v triple third derivative s equals 0. This is the general. So if we integrate on both sides, then we'll get negative sigma vs plus 6 is here. So this quantity can be written in terms of if we integrate, then we can write this as v squared s over 2 plus v double prime. Once we integrate, then the derivative decreases by 1, That means b triple prime will be here and double prime equals the integration constant a. Now if you multiply v prime s uh, by v prime s on all the sides, then we have this expression. We multiply a by v prime s and the left side by v prime s, and again integration will give us this expression. So again there will be a constant called we can call this as b, and b is a constant of integration. Now we investigate the above equation for those solution v which satisfies v prime and v double prime that approaches 0 as s approaches plus and minus infinity. By taking limit this s plus and minus infinity in equation 3 and 4, equation 3, equation 4 here, then we get a equals 0 and b equals 0. So now equation 4 reduces to, this equation now reduces to, we can write here a equals 0, b equals 0. That means on the RHA's right hand side we have 0. So now the simpler form of this equation is negative sigma v square over 2 plus v cube plus b prime is square over 2. So we can manipulate it, this, and then algebraically we can find the value of v prime is positive plus minus v sigma minus 2v to the power 1 over 2. For computational convenience we take minus sign above, and if you take the minus sign, then this v prime is nothing, just derivative v with respect to s, and this remains the same. Just take the minus sign here, and we can write this in terms of ds on the left side and dv on the right side, and the function of v here. Then integrate will give us s equals negative integration, where the different variable we have here g, which is the integration variable here, z. It starts from 1 up to vs, and we can integrate this, and then c will be a constant of integration. So now let's substitute g equals sigma over 2 secant hyperbolic square theta. Then by applying the derivative with respect to theta, we'll get this one. So ultimately dz equals this value. That means g sigma minus 2z to the power 1/2 will become this value. And as we know that the hyperbolic function has this identity relation, secant hyperbolic square s plus tangent hyperbolic square x is equal to 1. So apply this, and our final result will be g sigma minus 2s to the power 1/2 will be this one. That means dg over g sigma minus 2z power 1/2 will be negative 2 over sigma theta d theta. And again, by integration, we get s equals no integration. This our initial formula is here. S will become now s will be 2 over sigma, and then theta multiplied by theta plus c. That means s minus c equals 2 over sigma, square root of sigma and theta. Here theta is implicitly given by the relation here, sigma over 2 secant square theta equals vs. So ultimately vs will become sigma over 2 secant squared, secant hyperbolic square, square root of sigma over 2 s minus c, or this s is a real number. That means now our initial solution should be in terms of uxt, because the traveling wave solution is given by this profile, and with the velocity sigma here, vx minus sigma t, and replacing back uxt will be equal to sigma over 2 secant square, sigma square root of sigma over 2, and s can be replaced by x minus sigma t minus c. So this is the upshot, and it is a solution of the KdV equation for each c as a real number and sigma is a positive